All right, welcome everybody. So today we're going to try to answer the question, kind of what is an integral within the context of the physics class that we're in. And we're going to do this entirely by going through statements and questions that y'all actually had on the get ready question from last week. So this is a real statement from one of you. I've removed the names here so that we have a little bit of anonymity. But every question and statement that you submitted was a good one. So kind of just to kind of start off with some basic info that many of you referenced is that we know that integrals are basically the opposite of derivatives. We can think of an integral as an antiderivative. If I want, I can write down kind of what that looks like formally. If I have a function, let's call it y of x, I know that I can take the derivative of that function, right? dy dx. And that's going to give me some function, some new function, right? You might call it y prime or something like that. But I also know that if I take the integral of dy dx, so the integral with respect to x, that what I'm going to get here is y of x. I guess properly you'd want to put some limits on here, maybe 0 to x. And what you'd really get is y of x minus y of 0, right? This comes from like the fundamental theorem of calculus. Let's see, the other part of this that this statement brings in is that if I want to think about these two operations mathematically, integrals and derivatives, I can also think about them graphically. And if I think about a graph, maybe here's my function, y versus x. Let's make a y versus t this time. Let's mix things up a bunch today. So I know that I can find the tangent line to this graph, something like that or like that, and that the slope of that line is going to give me the derivative of the function. On the other hand, if I want the integral of the function, then I'm going to do something like try to figure out what the area under this curve looks like. I'll just kind of shade it a little bit. So that would be the integral of a function. That's kind of some math definition. We've used both of those definitions in physics, especially back in Physics 211. We'll be using integrals a little bit differently as we go forward, but that's some great stuff that many of you seem to know. All right, let's keep rolling. A big question that people had, this was probably the most common question and idea that you all expressed, is I know how I can use integrals to relate position and velocity and acceleration. We did that back in Physics 211. But how are we going to relate this to other quantities? And a few of you noted that there's other tricky things in here, like how power and energy are related. There's an integral in there. How energy or how work rather and force are related. There's an integral in there. I think I even saw one or two people talk about the impulse momentum theorem. There's an integral in that. So there's certainly other examples of integrals that we have seen thus far. The kind that we're going to talk about is more constructive integrals in this class. So the example that some of you referenced that I didn't grab a quote from was, if I know the density of an object, I can figure out how much mass it has. So that's the sort of integral that we're going to be using a lot in Physics 230. This was a great connection that y'all are making. So here was another kind of reference to this idea of area under a curve. Kind of how does taking an area of some region help me with physics? Not that often do we need to figure out areas in physics. But the reason for that is, maybe I'll bring back the graph here, is that in physics, we don't necessarily have y and x, right? You can see that I put y and t here, but I can really put anything I want on these axes, which means that maybe instead of putting y and x or y and t here, maybe I do put x down here, but up on this axis I put q, or maybe lambda would be a better thing to put up here, right? The charge density of the object. And now, even though in my graph I'm adding things up to get an area, in the real world, I'm adding up little charge densities. So what I'm really finding here is a charge and not an area. And we're going to do this with more and more advanced concepts as we go over the next week. So this was a really good connection to what we're about to set up. All right, there were a couple of additional really good questions here. Here it is. So what is the best way of not confusing integrals with derivatives and vice versa? If I think about, I've got x cubed and I want to take the integral. Is that going to be x to the fourth or is it going to be x squared? And kind of a related question is, how do I know what units to write for integral quantities? And these two kind of questions are actually connected to each other. I'm going to show you what that looks like right here. I'll do it first in kind of a mathematically abstract sense, right? If I were just to say have a function y of x, this in physics, if I'm choosing those letters for things, y is almost certainly a position. It's going to have units of distance. X is also probably a position, right? And so this thing, right, has units associated with it. If I integrate y of x dx, there's a couple of clues here as to what's going to happen with the units. One is that we have written this integral as a product of things, y times dx. And that means that if I know what the units of y are, and I know what the units of x are, then I should be able to know what the units of the integral are going to be by just multiplying those two things together. So in this case, if y has units of meters and x has units of meters, then the integral of y dx is going to have units of meters squared. The other clue you can look at is, and I've done a bad job of this so far in the video, but most integrals in physics will have limits of integration. So I will have like an x equals and an x equals up here on these two parts of the integral. And those both should be distances, right? Maybe from 1 meter to 4 meters, something like that. And of course, when we're being kind of lazy computationalists, we're just going to write that as integral from 1 to 4. But what we really mean is x equals 1 meter and x equals 4 meters. Excuse me. We can do this with a more advanced example. For example, we have been talking about charge density in class. And so if I were to write an expression like Q equals integral lambda dx, we can see this in action, right? The units of charge are coulombs. We already know that. The units of lambda are coulombs per meter. And we talked about that last week. And the units of x, or dx, are going to be meters. And we can see this equation working out now because those meters are going to cancel. Right? So it's a really nice trick to help you remember whether you have a derivative or an integral direction, because if I think about, maybe I want to take the derivative of x to the fourth. I think that was the example I used. Right? If I take the derivative of x to the fourth, that's going to take me down to x cubed, right? 3x cubed. So you can see that the units drop from being meters to the fourth to meters to the third. On the other hand, if I integrate, then I'm going to go up from x to the fourth to x to the fifth over 5, right? Now I've got units of meters to the fifth. And this is kind of encoded in the notation that we use. The integral has a little dx in it. You're multiplying by something with units of meters. The derivative, and if I write the derivative, dy over dx, that again, the notation signals to you what's going to happen to the units. You take the units of y and you have to divide them by the units of x. This was a really good question. I'm really glad a few people asked. I talked a little bit about this. Some people talked about how we can relate limits of integration to relevant information in a problem. We've already done one example of this in class. If I have a kind of bar with some charges distributed on it in some way, and I want to know what the total charge is, or the electric field, or any quantity about this object, the limits of integration are going to be related to what I'm trying to chop and add up, right? So I might integrate from one end of the rod to the other end of the rod. I wouldn't want to integrate over this region out here or this region out here because there's no charge there, right? And I wouldn't want to integrate in either of these two regions either, right? So that can be a strong clue to setting up your integral in physics. All right, I think there was one or two more really good questions. Yeah, other than correct notation, what is the reason for the little dx that shows up at the end of an integral? In your calculus class, you may just have been told that it's there to mark what you take the integral with respect to. And while like that feature is true, the little d does tell you what to integrate with respect to, it has physical meaning. One physical meaning we already talked about a couple minutes ago is that it carries units with it, right? That dx is something that has units of meters. If it's dt instead of dx, like we saw back in physics 11 when we were finding position and velocity by integrating, that dt held units of seconds, and it took meters per second squared up to meters per second, or up another step to just having meters. The other reason for it is, as people kind of mentioned, and I showed in my little graph, right? If here's my graph and I'm going to treat an integral as an area under the curve, what I'm really doing, if you remember back to your calculus, is I'm chopping this region up into little rectangles or trapezoids, and I'm adding up all of those little trapezoids. That dx physically is this little width of any one of these rectangles. And when I look at the integral, if this is, let's call it z this time, z of x, and this is x over here, when I write down integral z of x dx, this really is a product. I'm multiplying the height of one of these rectangles, z, by the width of one of these rectangles, dx. When I multiply those two things together, the integral symbol then tells me to add all of them up from the first line that I've drawn to the last line that I've drawn, right? So from some initial to some final value. Again, excellent questions y'all had. This one I just kind of threw in here for fun. This is my last one. How far can you integrate position, and what is it called? So we know we can take the integral of acceleration, we get velocity, we take the velocity integral, we get position. We can go the other way. We can take the derivative of acceleration. We didn't do it very much in physics 11, but you can take the derivative of acceleration, you get jerk, and then you get some more things that I can't remember. If you integrate position, there is actually a really abstract, obscure name for that. I have to remember it. Give me a second here. I believe it's called ABSMUTH, A-B-S-M-U-T-H. I think I got all of that right. You can check out a link on like Wikipedia or Hyperphysics for a little more detailed explanation of what it is. I don't think any other higher integrals have names, but I thought I'd end on a little fun note since things have not been fun in our world lately. So that is some answers from me to questions that you have had about what is an integral. In class this week and next week, we're going to really dive in to how these thinking of integrals in these ways can help us think about electric fields and electric forces.